What we call that, so the moles in a liter is molar concentration or molarity. So this is the number of moles of solute contained per every 1 liter of solution. When you were in grade 10, did you ever talk about using different hydrochloric acid that was maybe 1 molar or 6 molar? No? Okay. So molarity, or the capital M, is just how we represent moles per liter. So 1 M is moles per liter. So the definition refers to 1 liter of solution, not 1 liter of solvent. So that's an important distinction. We're not saying that we've got some salt plus 1 liter of water. We're saying that we've got 1 liter that contains our salt and our water. So it's the total volume of solute and solvent. Okay, this is our all-important formula, molarity. Number of moles of solute, so moles, per volume of solution, L. The short way to write that is C equals N over V, where C stands for molar concentration, and that we can call moles per liter, or M. N stands for number of moles. The more you go into chemistry or biology or sciences in general, the more you're going to see N representing number of something. So in this case, it means number of moles. V means volume. And it needs to be in liters. That's really important. So if you see it in milliliters, you could write moles per milliliter, but that technically wouldn't be molarity. That would be a different thing. Okay, so let's do an example. If we have 2 liters of a solution, so that's our V, we've got 5 moles of sodium chloride, so that's our N. We want to know the molarity, our C. So I'm going to set this up just like an algebra equation here. C equals N over V. N is 5. V is 2. And I end up with a concentration of 2.5 molar. Is that always how it's going to be? Oh no. It's going to get harder. I just like to pump your confidence up by giving you really easy ones at first, you know? Yeah. Yeah, Mikhail? Yeah. Okay. So shorthand symbol for concentration is a set of square brackets. So I will often use this. This is something that I will write quite frequently because I don't like writing out the word concentration. It's too long. I'm too lazy. So I might write, instead of this, I might write this. That is the same thing. So square brackets. So we can say NaCl equals 2.5 molar. Chemists, biologists, physicists, we all like to just shorten things up, make them easier. Okay, let's open up our textbooks and go look at page 97 for a minute. Okay. So page 97 talks about making up solutions. So this is a volumetric flask, and I'm just going to actually get one out to show you all. Okay, so these are a couple volumetric flasks. Aren't they pretty? They're so pretty. So they're, you can see that instead of, you know how on our graduated cylinders and stuff, there's a lot of different lines that show different measurements. On this here, there's one single line right around the top here, and that is 1,000 milliliters. On this one, there's a single line right there, and that is 250 milliliters. So for these volumetric flasks, you can't measure out a different amount of something. You're using the amount that's in your volumetric flask. So that's what this etched line is. Okay, so these are used to obtain accurate volumes of solutions. We can see a diagram of one here. They're manufactured in really specific volumes. Usually, they're accurate to about 0.1%. So that's pretty good. So the way that we actually make up an aqueous solution, so the solutions that we're going to be working with, we add the required amount of chemical. So if I had salt, I would add the salt to this first. And then I would add water or whatever my solvent was, and I would just add it up to this line here. So I'm not measuring out a separate amount of it. Like if I want 1,000 milliliters, I'm not measuring 1,000 milliliters and then pouring it here on top of my salt. I'm putting my salt in and then I'm pouring water in up until that line. Does that make sense? So the total volume, again, it's like the solute and the solvent combined. Okay, and then we cap it, we shake it a whole bunch, make sure it's dissolved, and then we add distilled water until the bottom of the meniscus, so that curve. Do you guys remember reading meniscuses? Menisci? I do not know what the plural for that is. Yeah, where you're looking at like the curved line. Okay, so you read that and make sure it's just touching that etched line. And we usually use a really small dropper. So it's a pretty precise and kind of intense thing to do. But I mean, it's not that intense, but it's a pretty precise measurement that we have to do. Here's an image of a meniscus here. So we want to make sure the bottom of it is touching the line, and that's to do with the surface tension of water. We make sure that that's where our volume is measured from. Okay, so I want you guys to look at these 3 questions and try to think of answers for them. So just, yeah, you can write them down or you can just think about them in your head, but have a look at page 97, questions 56 to 58, and think about those for a minute. About the answers to those. So in 56, you've been asked to make 1 liter. So that would be using this of sodium chloride solution, so salt solution. Why do you not add 1 liter of water first? Yeah. Exactly, yeah. So the sodium chloride does take up some space, and then you would end up with a higher volume than what you actually want. Good. Okay, 57, you're making up a solution. You accidentally add a bit too much liquid. The liquid level is 2 millimeters above the etched line on the neck. What should you do? What do you guys think? Yeah. Pardon? Dump it? Boil it. Oh, that's a good idea. Boil it so some of it comes out. Any other ideas or thoughts? Dump it out and restart? Yeah. What else could we do? Okay, why would we not just take some of it out? Yeah, so it's already the wrong concentration. Exactly. Okay, so yes, you could dump it out and restart. Boiling it would be a really good idea because you're just getting rid of the water. You wouldn't be getting rid of the salt. So you could actually boil it down a fair amount and then just like redo it and add water up to the line. So that would be a good solution. Or you could dump it out because it's salt water and it's not going to hurt anything. But when you're working with more expensive chemicals or something that could be harmful to the environment if you dump it out, it might be a good idea to try to get rid of some of the water. Okay, and then what practical problems might arise if you don't thoroughly mix it? So if you don't fully take it and like shake it around a whole bunch, what would be the problem with that? Any thoughts? Is it going to be equally concentrated throughout? No. So if you don't mix this, the bottom of it might end up being way more concentrated than the top. And then whatever experiments you're doing, they're not going to work based on your concentration. You're going to have way lower or higher concentrations. It's not going to be consistent throughout. Okay, so that's just a little bit of theory on solution making. All right, so we're going to find some more molarity problems. So I have got 8.5 grams of silver nitrate and water. And then I make the final volume 250 milliliters. All right. So what I need to do is figure out, if we look over here, can I just use grams or do I need to find something else? Moles. I need to turn this into moles. Okay, and then what about milliliters? Yeah, turn it into liters. Okay, that's a super easy one. I'm just going to move the decimal place over and just call it a day by doing that. Okay, and then the moles part, you want to do the calculation a little more thoroughly. So how many moles of silver nitrate do I have? So silver nitrate, the molar mass of it is 169.9 grams per mole. So if I have 0.850 grams of that, the number of moles I've got, so I can do 8.50 grams times, I need my 169.9 grams on the bottom per 1 mole, and I should end up with 0.0500 moles. Okay, so now we're going to do that concentration calculation. C, or molarity, equals which number goes on top, my liters or my moles? Good. 0.0500 moles per 0.2500 liters. Okay. And I'm going to end up with 0.200 molar. So moles per liter. You could write moles per liter, that would be fine. But know that it's also molar. Cool. You can rearrange this formula to be C. So this is what I gave you. C equals N over V. It could also be N equals CV. So it depends on what you're given. Sometimes you might be given concentration and you're trying to find volume. Sometimes you might be given moles and concentration and you're trying to find volume. Oh, I just said that. Anyway, you might be given two variables and have to find the other one. So you can rearrange the formula in any of these ways. Okay, so here's another example. I've got a 0.4 molar solution of sodium hydroxide. So there's my C. And I want to obtain 64 grams of NaOH. That will be my N, but I have to convert it to moles. Okay, I want you all to try this one on your own. So give that a go, and we'll go through the answer together in 3 minutes. The answer? No? Okay. Okay, make sure that you've got this many moles of NaOH before you go on. Oh, Amber, you have to sign. Thank you. All right. So let's just run through this. I need the moles of sodium hydroxide. So I've got 64 grams. My molar mass of it is 40 grams per mole. So I should have 1.6 moles of it. And then volume, to find volume, I'm going to go N over C. So I'm going to go 1.6 moles divided by 0.40 molar. What'd you guys get? Yeah, awesome. 4 liters. Yay. Okay. So that's how much I need in order to have 64 grams of sodium hydroxide in that solution. Alrighty. We're going to do one more example, and then I'm going to let you all do some practice, and I'm going to show you a demo afterwards. Okay, mass of sodium hydroxide contained in 3.50 liters of 2.2 molar sodium hydroxide. So for this one, we have got volume, we've got concentration, we are looking for mass in grams, which we're going to need to get to from having moles. So moles, and then we're going to need to go to grams. So I'm going to go moles, or I guess N rather, equals CV. So 0.200 times 3.50. And we should get 0.700 moles. Okay, so that's how many moles of sodium hydroxide I will have in that 3.5 liters of that concentration. Let's go from moles to grams now. Okay, so how many grams? What was the molar mass of sodium hydroxide? 40, awesome. Okay, so in order to get from moles to gram, we're gonna go 0.700 moles times 40 grams per 1 mole. That cancels out our moles. And what we end up with is 28.0 grams of sodium hydroxide. So that's our mass that's contained in that solution. So if we were to boil all of the water away, we would have 28 grams of sodium hydroxide left over. Okay. Any questions about this? We're feeling okay about it? So that's Na. NaOH. Okay. So this is what your practice is going to be. Page 98, these questions. There's a lot of them. This concept, how do you guys feel about this? Is this easier than stuff we've been doing so far? It's a lot to know, yeah, for sure. We're gonna push it to Friday because I don't think that we can get through this, have time to practice enough, and feel comfortable doing it tomorrow. So we'll push the unit test to Friday. Do you guys feel okay about that? Okay. Good. So tomorrow we will finish up these notes, and we will do some review. What I need you all to do, though, is make sure that you've done all of the questions up until this point. Make sure that you do these ones for homework. and you come into class tomorrow feeling comfortable with everything up until this, okay? If you're having a hard time with it, come in at lunch, stay in at lunch. Sound good? Yeah, so the multiple choice, and so the format of the test, there can be questions for sure about the theory and also questions about how you're actually doing the calculations. So yeah, there could be questions about the note stuff in there. Absolutely. Yeah, the notes,